slide that's up. So I'm going to hit record now. Good. All right. So before we get started, does anybody have any questions about anything? There seemed to be a little bit of confusion about the written homework. Just to clarify, for part B, there's a box there. That box is for the numerical answer. And then there's also a part C, which is asking you, basically it's for a written answer, and for part C, whether the first object bounces back, you would write that on your written solution that you handed to CrowdMark. So hopefully that's clear. I think if you try to put words into the box, Canvas will give you an error and let you know that you're not supposed to do that. Okay. Oh, you're welcome. You're welcome. That's not a problem. So what will probably happen is next week the sapling will also be due on Thursday, and the written will be due on Sunday, and then we'll try and get back into our regular cycle after the next test. Okay, so let's go ahead. If there's no other questions, let's go ahead and talk about some physics now. Okay, so we're talking more about rotation. We're going to do, this is all Chapter 8 content. I probably won't get through all of Chapter 8 today, so we'll have a little more Chapter 8 on Friday. There'll probably be one more topic to talk about before we move on to Chapter 9. So, and one of the topics we are going to talk about today is static equilibrium. So that's why I chose this comment, which is all about this comic, which is all about when static equilibrium failed. And as we're going to see, that means you're going to basically essentially you lose the laws of physics, right? When static equilibrium fails and you can no longer stay at rest. So as we'll see when we get to static equilibrium. So where did we end last time? So we ended with defining our average angular acceleration, which is our change in angular velocity divided by the time elapsed. And you measure angular acceleration in radians per second squared. Then once we had defined that, we said if you have constant angular acceleration, so something is rotating and either speeding up or slowing down at a constant rate, either clockwise or counterclockwise, then you can write a set of kinematic equations for rotational motion. And these are the three main kinematic equations here, where you've replaced linear position x with theta. So they're like our one-dimensional equations, but we've replaced x with theta, v with omega, and a with alpha. So we've replaced the linear quantities with the angular quantities. So the next thing we're going to look at is so if you do have an object and it is undergoing angular acceleration, what is the linear acceleration of a point on that rotating object? So if you looked at one of those point x's on the outside of our object, what would the acceleration look like? So here is, again, our rotating yellow disk, and now it has angular acceleration alpha. And if we look at a point with the little red x that's on the outside edge, a distance r from the axis, we can see if it's got as in this case, a counterclockwise angular acceleration alpha, then we get that we would get a tangential acceleration, linear acceleration. Just like we had a tangential velocity, now that tangential velocity is changing. Okay, so now we'll have a tangential linear acceleration. And the way you figure out what that is it's just like before. So we're talking again constant acceleration here. So the tangential acceleration here would be change in linear velocity divided by change in time. And then we just remember that our linear velocity for a rotating object for a point, a distance r from the axis, is just r times omega. And then change in velocity would just be r times change in angular velocity, because the r is not going to change. So it's just r times delta omega divided by the time elapsed. And then we say, oh, but we know what delta omega divided by delta t is. That's just our angular acceleration alpha. So we get that our tangential linear acceleration is just r times our angular acceleration. Just like we saw our tangential velocity was r times our angular velocity. So it's the same form as we saw for velocity. So that kind of makes sense. But then we say, okay, but this is not the only acceleration, because we go back and remember from uniform circular motion that anytime something is moving in a circle, there would be a centripetal acceleration. Okay, things are blinking for me. I hope they're not blinking for you guys. So I'm not sure why it's doing that. Okay, so we have a centripetal acceleration, as we know. So we will always have this as well. So there are two components to the acceleration here. And we know how to calculate centripetal acceleration. That's just our v squared over r. And then again, we're going to plug in that v is r times omega, our angular velocity. Okay, so not only is this object accelerating, but there's also an angular velocity, some instantaneous angular velocity. And so if you calculate this out, r omega squared, r omega, the quantity squared, divided by r, you get r omega squared for the centripetal acceleration. So we have two components here, right? And these two components always make a right angle with each other. Okay, and that's because one of them is along the radius of the circle and one of them is tangential to the circle. And the tangent and something along the radius will always be perpendicular. So these two vectors are always perpendicular. They're like an x and y component in a way. And so that means that the total acceleration of a point on a rotating object is a sum of those two vectors. Okay, remember acceleration is a vector. So we have the sum will be the sum of the two vectors. And then magnitude is easy in this case, because like I said, these two vectors are always at right angles to each other. So we can just use Pythagoras to figure out the magnitude of the total acceleration. It'll just be a square root of the tangential acceleration component squared plus the centripetal component squared. Okay, and that's true for a point, any point a distance r on a rotating object. So I don't know if there are any questions about that. It's kind of important to remember that these points on these rotating objects always have both components of acceleration. So I thought we would try a poll question on this. You might recognize this one from the sample test. So let's set up the poll here. Okay, so we've got our 4 choices there. So what do we have? So we have a fan. So the fan shown has just been turned on and is now speeding up as it rotates clockwise. So it started at rest and now it's going faster and faster clockwise. And the question is, what does the direction of the linear acceleration of the point x on the fan tip shown, what could that direction be? So you have 4 choices and only one of these is possible. The exact direction would depend on exactly how fast it was accelerating. But the question is, which one could it be? Could it be completely to the right, A? Could it be to the left, B? Could it be upwards, C? Or could it be downwards, D? Which of those are possibilities? So this is the total acceleration. So the linear acceleration would be a sum of the tangential acceleration and the centripetal acceleration. So this is an accelerating object. So it's going to have, so that point x will have both a tangential acceleration and a centripetal acceleration. So tangential acceleration is one component. In fact, I can probably go back. Well, I'll go back in a minute, sure. Well, I can go back now. Let's see if I can go back now. So just for a second, so you can see what that looks like. Okay. So here you can see this one's going counterclockwise. So that's what it looks like if you're going counterclockwise. So now we're going clockwise. Hopefully that's going to switch. No, the tangential acceleration is not equal to the centripetal acceleration multiplied by the radius. Let's go back one more time. So the tangential acceleration is r times alpha, which is the angular acceleration. Okay, and it points tangent to the circle. The centripetal acceleration is r v squared over r, or r omega squared, and that always points towards the center of the circle. And then your linear acceleration, the thing I'm asking you about, is the vector sum of those two vectors. All right, so we know what it looks like here for something accelerating counterclockwise and speeding up, say. So the question is, what if it's speeding up clockwise? Alpha is angular acceleration. So alpha is delta omega over delta t. So it's measured in radians per second squared. So it's how fast, how quickly the angular velocity is changing. All right, I think we're going to do 10 more seconds here. All right, 5, 4, 3, 2, 1. All right, we're going to show the responses here. So it looks like the majority, the vast majority, okay, about 2/3 of the class are going for D, that it could be downwards. So the direction of the total linear acceleration, the sum of the two vectors, okay, could be down. And then we have the next biggest group is voting for A, that it would be to the right. All right, so let's have a look at this one and see how you would figure it out. Okay, so like I just said, the linear acceleration is a vector sum of the tangential acceleration and the centripetal acceleration. So in this case, this is what it would look like. Okay, again, centripetal acceleration always points towards the center of the circle. Okay, so towards the axis about which the object is rotating. And tangential acceleration is tangential, is to the circle, to the circular path of the point, so at a right angle. And so you can see when you add these two vectors together, right, one possible option, depending on how big a tangential and a centripetal are, is that it points downwards. So the answer was D. Well done. Okay. So there was a question about whether tangential acceleration and centripetal acceleration will always have the same magnitude, and the answer is no. Their magnitudes are not connected to each other. Okay. So I might have drawn them so they look like they're roughly the same, but the magnitudes are independent of each other. Okay, because the magnitudes, just to go back to our previous slide, okay, the magnitudes, one is r times alpha, and the other one is r times omega squared. And so those are not necessarily the same. Omega could be very small. The object could be moving very slowly but have a very large acceleration, or you could have the opposite. It could be moving very quickly and have a small angular acceleration. Okay, so the other question, I'm going to go back now to this. The other question was if it was going in the other direction. So if it was going in the other direction, let's think about it. It would be, yeah, essentially could be B. It could be perpendicular to the left. Yes, yes, that's correct. Yeah, it could be that. That's right. Good. Any other questions on that? Well, if there are any other questions, I'm going to let Laura handle them so we can keep going. All right. So the next thing we're going to talk about is what's called torque. So if you want to make something accelerate angularly, so in order to cause an angular acceleration, a torque must be applied to the object. All right. So what we're going to see is a torque is the angular equivalent of force, right? If you want to make an object accelerate linearly, you apply a force, a net external force. If you want to make an object rotate, you apply a net external torque to the object. So what is torque? So you exert torques all the time in your everyday life. Every time you open a jar, open a door, anytime you swing something around, you move your arms and legs, you exert torque. So here's an example of a door, okay? And a door is a rectangular board that rotates about an axis through the hinge, okay? And so here's an example of a force F being applied to a door at a distance r from the hinge. And so what we do is we define a vector r that points from the hinge, which is the axis, to the point where the force is being applied, okay? And then we draw our force vector, okay? And then we draw a line through the force vector and a line through the r vector, and we look at the angle, okay, between those two, phi. And we see then when we put all three of those things together that the torque, we would say this force is applying a torque. What is the torque? The torque, which we use Greek letter tau for, is a magnitude of the r vector. So how far is the force being applied away from the axis? How far from the axis are you? F is the magnitude of the force being applied. And phi, again, is the angle between those two lines drawn through the two vectors. Okay, and so you take r times F times the sine of the angle phi. And that tells you how big the torque is. All right, so it depends not just on how far away you apply the force. The further away you apply the force, the more torque you get. That's why doorknobs are on the opposite side of a door from the hinge, okay, because then you need the minimum torque necessary to get the door swinging. If you pushed right near the hinge, if you haven't tried this, try and open the door by pushing next to the hinge. You'll discover it's really hard to open the door that way because your R would be very small. And then it depends on the size of the force being applied, and it also depends on the angle the force makes with that R vector. Okay, so all three of those are important. Before we talk about how those all work exactly, just to look at units. So you might notice that the units here is just length times force, so Newton meters. You may remember that a Newton meter is a joule, right? Because work was also force times distance, which is joule. Newton meters or joules. We tend to not use joules for torque. We use Newton meters because it's not an energy, all right? It's its own independent quantity torque. So we don't use joule for this, just to distinguish between the twos. Yes, so that's a good point, Kyle. So when you apply the force perpendicularly, okay, when phi equals 90, right, what's the sine of 90 is 1. That's as big as sine can get, right? And so then the torque becomes just the magnitude of R times the magnitude of F, and that's the maximum value for the torque. right? So if you want to get something rotating, you want to open a door, you should apply your force perpendicular to your door in this case, okay? To get the, basically that allows you to have the smallest possible force to still get it rotating. That's the most efficient way to exert your torque. So just to point out a couple of notational things to make it easier to figure out torque, there's two different things we can do. One is to define a quantity, which we're going to call the lever arm, or R perpendicular, which is the distance between, the perpendicular distance between the hinge, in this case, which is the axis, and the line that goes through the force. So if you draw a line through the force, and then you basically make a right triangle with the line through the force, the R vector, and this third line, R perpendicular, okay, we call that distance, okay, that perpendicular distance from the axis to the force line, we call that the lever arm, okay? And if you look at that right triangle there, between R perpendicular, the line through the force, okay, and R, you can see that the length of R perpendicular, the length of the lever arm is just R sine phi. Okay, and then you go look at your formula and you say, oh, well, R sine phi is in my torque formula. That means I can rewrite torque as just R perpendicular times F. So torque is, and you often hear people talk about torque being the lever arm times the force. Okay, so that's where that expression comes from. All right, that's correct. It's just, so the lever arm, that R perpendicular, which depends on phi, right? And so it will vary depending on the angle the force is applied at. So that's another way to think about torque, is lever arm times the magnitude of the force. A third way to do this, or another sort of way to rearrange our torque expression, is instead to look at the force perpendicular to the line through R. So this is kind of doing the opposite thing. Instead of looking at the R perpendicular to the line through F, let's look at the force perpendicular to the line through R. Okay, so the component of the force perpendicular to that line, we're going to call that F perpendicular. And again, we have that right triangle there, so that F perpendicular is F sine phi, because it's opposite the phi angle. So you can also write that the torque is equal to R, which is just the magnitude of that R vector, how far you are from the axis, times the perpendicular component of the force. And this is often the easiest one to picture. When you have a bunch of forces, I tend to use this one more than the other one, because when you have a bunch of forces acting, it's easy to picture what the perpendicular component of those forces are. And then you just take the perpendicular component times your R, and you'll get the torque for each of those forces. So I'm going to show you a couple examples of this in a minute. All right, so that's a very useful convention there. So are there any questions on that? Like I said, I'm going to do some examples, and hopefully the examples will be helpful. Before we do an example, though, I thought we would do a poll question. So let's start this one going. Okay, so this one, we're going to do this one pretty fast, because I think you guys will be able to figure this one out. Basically, in which of the cases shown is the torque provided by the applied force about the rotation axis? So this is another door with a doorknob. Okay, so in which case is the torque the biggest? Okay, so you've got, and for all cases, the magnitude of the applied force is the same. So the magnitude of FA equals the magnitude of FC equals the magnitude of FD. I don't know what happened to FB. I don't remember from this example why there's no FB. Okay, but the idea is you got three forces. They're all the same magnitude, but they act in different directions. Okay, they're all acting at the same point on the door, which one is creating the biggest torque? You're getting super hungry? Not sure why you're getting hungry. All right, I think we're going to do 5 more seconds on this one. So go ahead and guess if you're not sure. Is the screen blinking for you guys? The screen is blinking for me, and I'm not sure what's going on. No? Okay, good. It must just be my computer then being silly. Oh, yes, some people are getting blinking. Some yeses, some nos. All right, so 5 more seconds here. 5, 4, 3, 2, 1. All right, let's see what everybody thinks. So we have lots of consensus today, and the vast majority of people think that the answer is A, okay, that it's the force that's acting perpendicular to the door. And that is in fact correct, because as we just saw and we talked about in the chat, we know torque is RF sine phi. So the force that's going to be at 90 degrees, that has a phi equals 90 degrees, right, is the one that will exert the biggest torque, because sine of 90 is 1, and that's the largest sine can be. Okay? So sine can't get any bigger than 1, right? And so when phi equals 90 here, and this is a case similar to work where our angle will be somewhere between 0 and 180. We'll never go above 180, so we only have to look at sine between 0 and 180, right, which is always positive, and ranges from 0 to 1. So our answer is A. Okay? It's interesting to look at. What do you think the torque force D would exert? What torque would force D exert? 0, good, yes. No torque at all, right? Okay, if you ever try to open the door by pushing on the end, you'll discover it doesn't work, right? You can't push on the end, you can't pull on the end. You have to have a component perpendicular to the object to make it rotate. Okay, FC will make it rotate, right? Well, unless you have sliding doors. Yeah, that's a completely different situation, of course. So, okay, so now we're going to look at what's called Newton's second law of rotation. So this is basically, we've already seen Newton's second law. Newton's second law is our net force is equal to mass times the acceleration of an object. So similarly, the net torque acting on an object is equal to its moment of inertia about the axis times its angular acceleration. So it looks like this. Okay, so remember that moment of inertia is the quantity that acts like mass for rotation. Okay, and it's defined about a given axis. Okay, so you have, in all of these problems, you're going to have to choose an axis. They'll usually tell you an axis. Most of the time, the axis will be about the center of mass. Okay, and then you take that rotational inertia, that moment of inertia, times the angular acceleration, and that will tell you the net torque that's acting on the object. Okay, and what we're going to see is that some torques cause objects to rotate clockwise, and some torques cause objects to want to rotate counterclockwise, and we're going to give those different signs. We're basically going to say a torque that causes something to rotate counterclockwise is positive, and a torque that causes something to rotate clockwise is negative. So because torques, right, are going to compete against each other to tell you which way an object will rotate. So just to have a quick look at units here. So torque units were Newton meters. Moment of inertia units are kilogram meter squared. Alpha units are radians per second squared. And again, we are going to drop the radian. So this is another example where to get the units to work out, right, because radian is a dimensionless unit, you can drop it. And so then you end up with just kilogram meter squared per second squared, which you probably recognize as a joule, but it's also a Newton times meter. So you can see that the units work out for our second law of rotation. So I thought we would do an example of this. Okay, so imagine that like this is a very thin stick. Okay, say it's sitting on a tabletop, and you've got an axis that's 2.5 centimeters from one end of the stick, and you're exerting a force F on that end of the stick. Okay, in this case, it's downwards on our page. Okay, it could be towards you if this was on a tabletop. And that's causing a mass at the other end of the stick, 31 centimeters from the axis, to accelerate, to have this tangential acceleration here, okay, of A. And so what we're going to figure out is a couple different things. If the mass is 3.6 kilograms, and if the magnitude of the acceleration is 7 meters per second squared, we're going to assume the rod is massless, okay, or very small compared to the mass of the blue ball. And there are no other forces acting, or at least no other unbalanced forces acting. We're going to figure out what is the torque applied by the force, and what is the magnitude of the force. So that's what we're going to do. All right, and so now I'm going to see if my document camera, I think I managed to get my document camera to sort of work. So we're going to give it a try. Let's see if I can get this. So I'm going to use the app that comes with the document camera this time. And so hopefully that looks okay to you guys. And it's not too out of focus here. Okay. So what did we have? I'm going to just draw it again so we know what it looks like. So we have a stick. We had the force F this way. We've got our mass M, and we've got an acceleration A. Slide that down so you can see that. Okay, and we were told that this distance was 31 centimeters, and this one was 2.5 centimeters. Okay, so that's what our scenario looks like. Okay, so how do we figure out, the first question was, what is the torque applied by the force? Okay, and we're going to go for the magnitude of the torque. All right, we can see here that this thing would rotate clockwise. If you pull down on the force, this thing would rotate up this way, right? And this would rotate down that way around the axis. Okay, so we're going to try and figure out the magnitude of the torque here. This would actually be a negative torque, right? Because, just to write that down, because this thing would go clockwise. Okay, so we have two ways to figure out torque, right? We know that the magnitude of the torque could be RF sine phi. And we also know that the net torque equals I alpha, right? So there's two different ways to figure out torque. All right, we don't know F. So since we don't know F, okay, we can't actually figure out this. We can't do it this way. So we have to do it the second way. Okay, we have to use our I and our alpha, and we can figure out alpha because we know A up there. So let's actually write down what I forgot to write down everything else. We know that our mass is 3.6 kilograms. And we know that our acceleration, that tangential acceleration, is 7 meters per second squared. Okay, so like I said, we're going to use net torque equals I alpha. Okay, there's only one torque being applied here, the torque by the F, so the magnitude of the torque. So now, we were told the rod is massless, so the only I is the I of the big M of the ball. Okay, and that is just equal to mr squared. It's the size of the mass times how far away it is, where r is just this distance here, the distance from the axis. So r is going to be our 31 centimeters. Okay, that's the I, so it's that times alpha. Okay, and then the next thing we're going to remember, okay, is that alpha is related to A. We know that A equals alpha R, right? So that means that alpha equals A over R, right? So we're going to plug that in here, A over R. And we can cancel out one of those R's, and we just get M times R times A. That'll be the size of the torque. So now we can plug in our values, 3.6 kilograms times R, which is 0.31 meters, times A, which is our 7 meters per second squared. And what do we get? We get that the magnitude of our torque is 7.8 Newton meters. Okay, so that's the torque required to have that mass m at a distance of r accelerate, have a linear acceleration. Okay, well, this is the tangential acceleration, right, of 7 meters per second squared. So that's part A. Then we can figure out part B. Part B is trying to figure out what's the magnitude of the force. Okay, so what do we figure out now? So now we can use the second formula. The torque equals RF sine phi. The torque will be 7.8 Newton meters. Okay, but now we have to be careful. Now what's the R going to be? Okay, now the R is different here, right? Because now we're looking at the distance, the forces from the axis. Now our R is going to be 2.5 centimeters. Okay, so this is 0.025 meters. We're going to solve for our F. And what is phi in this case? Anyone want to tell me what phi is in this case? Yeah, it's 90 degrees, good. Which means that the sine of 90 here, that's just 1, right? And so now we can solve for the magnitude of that force. Okay, yeah, if they draw it tangential, if they draw the acceleration tangential, then you know it's a tangential acceleration. And so what do we get? We get a force of about 312 newtons. I wouldn't know. These phi's are between 0 and 180. Okay, so in this case, the R is this way. So here's the line through the R. Here's the line through the F. Okay, and you always want to use the angle that's less than 180. Okay, so that you have a positive value. Okay. All right, so we're talking about something that's horizontal here. All right, which is why the mass isn't causing a rotation. All right, we said no other forces were acting here. All right, so if you have more questions, hopefully Laura can answer them. Okay, but the idea was there were no other forces acting, so that's why the mass. If this were a vertical scenario, then that mass could cause it to drop. And so that's actually what we're going to do next. Now what we're going to do is look at scenarios where there is gravity involved. And one of the most common scenarios that you guys might run into, especially if you're in kinesiology, is looking at how your muscles make your arms and legs move. Okay. So, so here you can see, for example, here's your arm, and you got your triceps muscle and your biceps muscle. And the main thing to remember about muscles, okay, is that they pull, they don't push. Okay, so like with our arm up here at the top, the biceps muscle would pull to help your arm raise, but the triceps muscle, which pulls on the other side of the axis, is what pulls when you lower your arm. Okay. So, and you can see for the first picture here, A, okay, they've drawn in all the possible forces that could be acting if you're holding your arm horizontally and trying to hold on to a ball. Okay, and what can you see here for the forces that are acting? There's an upwards force of the muscle that's holding your arm upwards, keeping it in place. There's a downwards force of the basically gravity acting on the ball you're trying to hold, and that acts at the ball, a distance from the axis. And then there's the mass of the arm itself acting at the center of gravity. And then there's also a force, okay, so this is sort of the force on the arm itself. There's a force of the joint pressing down. There could be a force pressing down. And what you're going to see is it's going to depend on the scenario exactly which way that joint force points. Okay, and so what I thought we would do is do an example, because the best way to learn how all of this works is to look at an example. Okay, and when you have a scenario like this where you're trying to hold something at rest and stop it from both translating and rotating, then we say what you have is static equilibrium. Okay, so the conditions for static equilibrium are that the net force acting on the object is 0 and that the net torque as acting on the object is 0, so that you have no motion, no linear motion, and no rotation. Okay, and so what I thought we would do is an example of this, another kinesiology. This is an actual kinesiology example that one of the kinesiology professors gave me a while ago. So I thought it would be good for you guys to see what it looks like in the kinesiology context. Okay, but this is in fact just a static equilibrium physics problem, okay, applied to muscles in your body. So it says, so what do we have? It says we have a single equivalent muscle representing the forearm flexors, okay, which are those muscles in your upper arm, I believe, that keeps your arm, helps your arm move up and down, the lower arm move up and down. And it's capable of producing 1,500 newtons, lots of force. And its tendon attaches 0.03 meters, 3 centimeters, from the joint axis of rotation, and you can see it attaching there. Assume the line of action of the muscle, so that's the direction of the force the muscle exerts. Assume the line of action of the muscle is parallel to the humerus, which I believe is this upper arm here. Okay, so this is kind of a schematic where you've got your upper arm and your lower arm, and you've got a muscle force acting 0.03 meters from the axis. And there's two questions they're asking. The first question is, what torque could this muscle produce at a relative joint angle of 150 degrees? That's supposed to be 150 degrees there. Okay, and how much force does the muscle exert to support the arm in a horizontal position if the mass of the arm is 3 kilograms and its center of mass is located 0.15 meters from the elbow joint? All right, so I'm going to get as far through this as I can for you guys. And then whatever we don't finish up today, we can finish up next time. All right, so we're going to switch to the document camera again. Hopefully this will work for you guys. Okay, so what did we have? So we have an axis. So I'm going to draw it again as a stick figure. The axis is your joint. Okay, and we have a force. acting a distance of r equals 0.030 meters, okay? And they told us that this was 150 degrees, right? Okay, and that's our force. And the first question was basically, if the magnitude of the force is 1,500 newtons, what is the torque? What is the magnitude of the torque? Here. Okay. So in this case, I'm going to use torque equals F perpendicular R. Because like I said, it's usually pretty easy to figure out F perpendicular. Okay. So what's F perpendicular here? It looks like this. Right? It's the component of the force. Okay. Perpendicular to the arm, and you have two choices to figure that out. You can either recognize that this angle is 30 degrees here, right? Because that adds up, and then F perpendicular is just F sine 30, right? Or you can see that this angle is 60 degrees, right? Because 60 plus 9 equals 150, and you could do the cosine. So either one of those works. I'm going to write it as F sine 30 degrees times R, and then we can calculate our torque. So 1,500 newtons times the sine of 30, which is a half, times R, which is 0.030 meters. And we get a torque of 22.5 Newton meters. Okay, seems like a small torque given how big the force is, but remember the lever arm is very small, right? Our distance there is only 0.030 meters. Okay, so that's how much torque you could exert, okay, at that angle. The next question was, how much force does the muscle exert? So we're looking for muscle force now. Okay, to support the arm in a horizontal position. And then they give you the mass of the arm and they tell you where the center of the mass of the arm is. So now what you need to do is you draw one of these extended body diagrams. So it looks something like this. So here's our arm again. I'm going to draw it very long this time. Here's our force, again, acting at a distance, right, over 0.030 meters, right? That's the distance here, meters below there, right? But now we also have to worry about the fact that our arm has mass. So here is the weight of the arm acting at the center of mass, okay, of the arm. So I'm going to put in a y-axis and an x-axis, because to apply static equilibrium, okay, you need to balance the forces and the torques, okay? And I think we're only going to just have time maybe to set this up, okay? And then we will do the rest of it next time. So, so one thing I want you to notice right away is that notice how the force F points to the left, and there's no other force pointing to the right to balance it. And that's because we haven't drawn in all the forces. There has to be a third force, which I'm going to call force joint, where a component of which is balancing the force F. Okay, so there has to be another force here acting. Okay, they didn't mention it in the question, but we know it has to be there, because if that force wasn't there, then we couldn't balance the forces, because our requirement is that the sum of the forces in the x direction must add up to 0, the sum of the forces in the y direction must add up to 0, and the sum of the torques must add up to 0. Those are our requirements for static equilibrium. So we've run out of time. So I think what we're going to do is we're going to do this problem next time. So if you want to try it yourself at home, Okay, given that the arm mass, they did give us the arm mass, was 3 kilograms. Okay, and that the last thing they gave us was that this distance was 0.15 meters. So if you want to try it at home, I recommend trying it at home, and I will do this at the beginning of class next time. Okay, so we're going to stop there. And I'm going to stop the recording.